Hello friends, now today's lecture we will start with we will discuss in detail about plastic deformation. So, during uniaxial deformation we have already seen through our tensile test that after yielding material undergo plastic deformation. So, we want to understand this whole process of plastic deformation and how it takes place. So, to understand that what happens at the yielding, so we will look at the one of the criteria that is Tresca criterion. So, if you remember in your strength of materials course, you must have gone through different yield criteria, and in that one of the yield criteria is Tresca criterion. Okay, and the Tresca criterion says that whenever the maximum shear in the system reaches the shear strength of the material, shear yield is strength under shear of the material, then the yielding will takes place. Okay, so you can see that there are three principal stresses shown here, sigma 1, sigma 2, sigma 3, and the maximum shear stress will be between sigma 1 and sigma 3. So, algebraically sigma 1 is maximum and sigma 3 is minimum. Because we are talking about 3-dimensional state of stress here, you can see that I have drawn 3 Mohr circle here. So, one between sigma 1 and sigma 2, another between sigma 2 and sigma 3, and one between sigma 1 and sigma 3. So, tau max will be given by sigma 1 minus sigma 3 divided by 2. Okay, that is the radius of this circle, where sigma 1 and minus sigma 3 is the diameter of this circle. So, when this maximum stress in the system, the maximum shear stress in the system reaches the yield strength of the material under shear, then the yielding will takes place. So, yield strength we have seen till now under tensile mode, and there we call it as sigma y. Okay, and this yield stress is under shear. So, if you apply a shear stress on the material, then also yielding will takes place. So, for that a torsion kind of experiments are there, where you give a torsion stress or torsion strain, and the yielding will be taking place at under shear stress condition. Okay. So, there is a relationship between the whatever yield strength you get from simple shear kind of experiment and the tensile experiment. Okay, that will be k equal to sigma y by 2. Okay. So, this is what, and actually what happens under yielding we can see from this animation here. Okay. So, I am trying to show you that I am increasing the stress on the system. Okay. So, this is how I am increasing the stress in the system, and you can see at some point when my maximum shear stress now reaches the yield strength under shear, or shear yield strength of the material, then the material will yield. Okay. So, if you see the angle which tau max makes with the sigma 1, okay, here that is around 90 degree in Mohr circle. So, in physical space it will be half of that, that is 45 degree to the principal stress. Okay. So, if we want to see it in terms of our experiment, okay, where suppose we have taken a sample like this, a cylindrical sample, and I am applying stress sigma 1 in this direction, it is a uniaxial deformation. So, sigma 2 and sigma 3 both are 0. Okay. Then my yielding my yielding under shear should takes place when my sigma 1 by 2 is equal to k, that is the shear strength of the shear yield strength of the material. Okay, and that is also we have seen that this tau max acts at 45 degree to sigma 1. Okay. So, if this is sigma 1 at 45 degree to that, my maximum shear is acting. Okay, and when it reaches the yield strength of the material, or yield strength of the material under shear, then basically this upper part will slide. Okay. So, maybe I can just show you an offset here, maybe it will be something like this, and here also there will be an offset. Okay, and it will be like this. something like this. In this particular plane it is slided by some distance. Okay. So, there is a slip which is taking place, okay, and by which the upper part has slipped with respect to the lower part at 45 degree to sigma 1. Okay. So, when I reach the yield point, my material will shear, okay, and that is how it shears. Now, at atomic scale, okay, till now we were considering this whole system as a continuum. Okay, we were not saying that anything is there and it is a continuum. There are no at atomic scale there is nothing there. Okay, but at atomic scale, when we want to understand the deformation, actually there are atoms. Okay, and the sliding place, and if you have a shear stress acting on the system, then the sliding takes place of one crystal plane over another, okay, and that is how you can produce the slip. So, this upper part has slipped with respect to the lower part. Okay. So, if I want to know that how much stress will be required for that, okay, so what will be the maximum stress, shear stress will be required to do this kind of process, okay, that will be equal to, if I do a theoretical calculation, I am not doing the total derivation of this. You can look at there are a lot of books in which this kind of derivation is given. Okay. So, basically the maximum shear stress which is required to do this kind of slipping process will depend on the G shear modulus. B is basically the slip distance. Okay, my upper plane has shifted by 1 atomic distance here. Okay, D is the distance between the, or let us say I show it here. Okay, interplanar spacing. Okay, D, and some constant 2 pi. Okay, which I can replace since in usually cubic material B and D are very close to each other. Okay, the values are almost in the same order of magnitude. Okay, so I can just remove that. So, my tau max is now equal to G upon 2 pi, and now I can use some conversion constants are there between the Young's modulus and the shear modulus, okay, which uses the Poisson's ratio nu here. So, it will be E upon 4 1 minus nu pi. So, ultimately you will get some value which is E by 17. So, this is the theoretical shear strength of the material. Now, if you compare the theoretical strength with the experimental shear stress, okay, for example, for silver it is 12.6 gigapascal, okay, but in experiments when when people found out, they found that it is only 0.37 megapascal. So, there is almost like 3 or 4 order of magnitude difference. Okay, let us say for copper it is 19.6, but experimentally it is only 0.49. Okay, so what is the reason for that? Already when we were discussing defects, we said that this difference between the theoretical strength what we calculated by equation in the previous slide and what you get experimentally, the reason for this difference is that there are some defects present in the material which are called dislocations, okay, and that brings down the shear strength of the material. Okay. Now, when you talk about shear, okay, then is there any preference for certain crystal planes or direction? Okay. If you look at this equation here again, tau max equal to Gb by 2 pi d, where B is your slip distance and D is interplanar spacing. Okay. If you remember when we were discussing about crystal structures and about planes and direction, okay, we might have discussed that the slip distance is minimum for closed peg direction in closed peg planes. Okay. For example, there is a 111 plane in FCC is shown here, okay, and in the 111 plane of FCC, this is the best pecking you can get for a spherical atom. Okay. If you take any spherical object, okay, so best pecking you can get when you place another sphere in between the two here like this, is not it, and so on. Okay, so this is going to be the best packing, you cannot get better packing than this, and that is packing you see in the 111 plane of FCC arrangement. Okay. So, if you see this 111 plane of FCC, okay, you can see in this 101 direction or 110 type of direction of FCC, you have minimum distance between the atom. So, this atom when it slips, it goes to the next position here. Okay, so this is the distance it is going to travel. Okay, so this, as I told you, you cannot get best packing than this. That means this is the minimum distance atom has to travel, and that is equal to your slip distance. We also discussed that you have maximum spacing, interplanar spacing d when you are talking about low index planes. Okay, so low index planes are 100, 110, 111 and so on. So, in this direction now indexing is increasing. So, this will have the maximum d spacing, okay, and that then d spacing will decrease in this direction. Okay. So, of course, but these two planes are not the close pack planes. So, the best close packing we find in 111 plane, and of course, d spacing will also be quite high in 111 plane. So, these type of planes are the preferred planes where the slipping is going to take place. Okay. So, not all at crystal planes and all crystal direction take part in the slipping process. There is a preference for shear during shear for certain planes and direction, and those planes are the close pack planes and the directions are the close pack direction. Okay. And that is those are going to have the minimum slip distance and maximum interplanar spacing. Okay. For example, slip system in different crystal structures, if you want to see, just another I want to tell you that in FCC cubic crystal, okay, this is 111 plane, you will get 4 111 planes like this. Okay. When we were discussing indexing of planes and direction, we discussed about that you will get 4 of these 111 planes, and in each 111 plane you will have 3 110 directions. Okay. So, 3 110 type of directions will be there. Okay. So, in combination, if you look at the slip system, there will be 12 slip systems. Okay. So, that is what we want to tell you in this next slide, that slip system is a combination of plane and direction lying in the plane. So, direction which is lying in the plane and the plane, what is the combination of that. So, slip plane in FCC we have told you that it is 111 plane, close pack plane. In slip direction is 1/10 type. So, now number of non-parallel planes are only 4, slip direction per plane is 3. So, number of slip system is 12. In BCC, of course, none of the planes are the close pack planes. Okay. So, only there is closest to close pack arrangement, that is what you see. So, the closest to close pack arrangement you get in these 3 type of plane, 110, 112 and 123, and these are the close pack direction. But direction is, of course, there is a close pack direction is available. Okay. So, number of non-parallel planes for this type is, these numbers are there, then in each slip direction per plane are also given. So, total 48 systems are there in BCC, okay, whereas in FCC there are only 12. Though there are more slip system, it appears there are more slip system available in BCC, but you have to keep in mind that these are not the close pack planes. So, though their number is high, but still they are not as effective as these 12 planes in the FCC system. In HCP, of course, basal plane will be a close pack plane, and 11/20 direction will be close pack direction. So, there are 3 actually which satisfy the close pack plane and close pack direction condition. The other 2 are not are similar to BCC type. Okay. So, here also you get 12 systems. Okay. So, in this you can see that FCC has very efficient slip system. Okay. Now, looking at the slip process, okay, slip process require extent of slip in single crystal depends on magnitude of the shear stress, as we have just discussed when we were discussing Tresca criterion, that what is the maximum magnitude of shear stress. We know that shear stress required for slip process. Okay. We also know from stress analysis that shear stress is maximum at 45° to principal stresses, as we discussed during Tresca criterion. Then is slip always going to take place at this angle? So, this is the question which we should ask ourselves, that if this is the case, okay, I am applying the stress like this, which is sigma 1, okay, principal stress in this direction, then according to the Tresca criterion, at 45° I should get the maximum shear stress. So, now the question is whether my material is going to slip in this 45° direction or not. The twist in the tail, okay, is that the geometry of the crystal structure, and now we also know that slip will take place at the close spec plane in close spec direction, which may not be at 45°. Okay. If you look it as a continuum system which does not have these atoms and it is a continuum, okay, then this analysis actually tells you at 45° you should get the slip process. Okay. But now we also know that which planes are going to take part in the slip process. So, in FCC for example, we know that close spec planes and close spec direction are going to be the one where the slip is going to take place. So, it is not in any direction you will have a slip. So, in 45° direction of the maximum shear, if my 111 plane is not lying in that particular direction, then slip is not going to take place in 45° direction. Ultimately, what the slip is going to take place only in the plane which is 111, how it is aligned with the maximum or how it is aligned with the shear stress direction. Okay. Hence, it will depend on orientation of the active slip planes with respect to shear stresses. Okay. So, basically this is what we are saying, that ultimately atomic arrangement is the one which is going to decide whether you are going to get deformation or slip process in that particular direction or not. Okay. So, to resolve this problem, okay, Schmidt, one scientist, he proposed that slip begins when the shear stress on the slip plane in the slip direction reaches a threshold value called critical resolved shear stress. Okay. So, he said that when the resolved stress in that particular plane and in that particular direction, when it reaches a critical value, then the shear then the slip process will take place in that particular plane and direction. Okay. So, this is what the idea is now. So, instead of that 45° which is given by the Tresca criterion, okay, ultimately we have to see that whether my close spec plane and close spec direction are lying in that particular direction or not. Okay. So, first we will resolve the shear stress. So, now we are resolving the shear stress here. So, let phi is the angle between normal to the close spec plane and tensile axis. So, this is my plane. Okay. Now, this may not be at 45° to the principal plane, principal direction, but it is making some angle with the tensile axis, and that I am calling as phi. So, phi is the angle between normal to the close spec plane, this is my normal, and tensile axis. So, this angle is phi. Lambda is the angle close spec direction makes with the tensile axis. Okay. And this lambda here is the angle which the slip direction is making with the tensile axis. Okay. The area of the slip plane inclined to the angle phi will be A upon cos phi. Okay. Component of axial load acting in the slip plane in the slip direction is P cos lambda. So, now basically we are resolving the load P, okay, in these two directions. Okay. So, I think instead of F I will say it as P, because that is what we are saying. Okay. So, it will be P the area, this is my area A naught, okay, but my shear stress is acting on the area which is given by AS. Okay. So, the area which I am resolving here, okay, will be A upon cos phi, okay, that is what I am writing there. Let us say that this is A naught here, and the slip direction is your tensile. I am resolving the P for stress in the direction of slip. So, this will be P cos lambda. Okay. So, now my shear stress is acting in this plane in this direction. Okay. So, and of course, this direction will be lying in the plane. So, this is going to be of course going to be shear stress. So, shear stress is acting in this plane in this direction, and plane is given by A naught divided by cos phi. So, my resolved shear stress will be P cos lambda divided by the area. So, this is my force, resolved force in that plane, and this is my area of that plane, okay, and that will be P A upon cos phi into cos lambda. Okay. So, this cos phi cos lambda is the Schmidt factor, okay, not this one, okay, only up to here. So, cos phi into cos lambda is your Schmidt factor. Shear stress is the maximum when phi and lambda both will make angle of 45 degree. Okay. If I take 45 degree and 45 degree here, this is going to give me the maximum shear stress, and it will be 0 if phi is equal to 90 degree. So, phi 90 degree means the plane is almost the plane is parallel to the tensile axis. Okay. So, it cannot, you cannot have shear in this direction, because in this direction your maximum principal stress is acting. Similarly, delta 90 degree means delta 90 degree becomes 90 when the plane is in this condition. So, now principal plane is acting like this. So, in this plane now shear stress cannot be maximum, okay, because only the normal stress is acting there. So, in these two configuration of planes, okay, my shear stress is going to be 0, and it is going to be maximum for phi and lambda equal to 45 degree. Okay. So, tau the resolved shear stress is P by A cos phi cos lambda. Let us say I call it as A naught, because in the figure it is written as A naught. So, it is sigma cos phi cos lambda. So, P upon A naught is equal to sigma into cos phi cos lambda equal to sigma into m. Okay. We are representing this factor as m here. The slip system having largest Schmidt factor may slip. Okay. So, now what we will do is we have 12 slip system, 12 arrangement of 111 plane and 110 direction. Okay. Now, we do not know for which one this is going to be maximum, the tau RSS. Okay. So, what we will do, we will determine this particular factor for all the planes with respect to the tensile axis, and for whichever it is going to be maximum, okay, that is that system is of interest to us. So, condition for slip is when largest Schmidt factor. So, largest of this 12 whichever comes, okay. So, out of this 12 one will be the largest obviously. So, when the largest Schmidt factor reaches critical value for yielding, so that yield stress, so then it this tau RSS become tau CRSS, critical resolved shear stress, when I am replacing sigma by sigma y now, okay, and cos phi cos lambda the m when it is the maximum for whichever is this. If this factor reaches the critical resolved shear stress, then the slip is going to take place. Okay. So, now you can understand that idea of 45 degree to the principal plane. Okay. Now, we have brought in the idea of crystal planes and crystal direction in this whole thing. Okay. And now, we are able to tell you that which planes are going to take part in the slip process. So, when we will do the assignment, this will be more clear to you that how we can use this relation to find out this aspect. So, thank you, and we will take the another lecture on plastic deformation, okay, where we will discuss about other mechanism of deformation, that is twin, and we will also see in slight detail that how the deformation takes place in the single crystal. Okay, thank you.